Hi, we are Ceres, and your robotics team from Universidad de los Andes, Bogotá, Colombia. We're a team of 14 members studying engineering, science, and design-related majors. We've been working hard for the past 8 months to present you Project Venture.
The core of Venture are its motors. Starting in June 2024, we made them from scratch, from testing windings and analyzing performance parameters to designing an internal cyclodial drive to make them compact and powerful. Leveraging 3D printing for rapid prototyping, we are now converting them to steel and aluminum parts. Controlled with an all-drive S1, they are what make us move.
Each wheel is powered by our own motors. Made from TPU, they will feature a fine-tuned U-rate infill for optimum grip. Additionally, they have a sand footprint designed to enhance traction on loose surfaces, ensuring reliable movement and control.
To ensure that the rover can overcome the harshest terrains, we designed a rocker system that keeps our wrist motors vertically aligned, at all times using a 4-bar linkage in each wheel. Spring-loaded shock absorbers handle small bumps and holes, while a linear actuator in each wheel allows us to independently control the height of each wheel, leveling the arm and extraction tool on uneven terrain. The rockers are attached to the aluminum sheet folded chassis through a central support beam placed at the rover's center of mass, balancing the arm and electronics load to optimize speed and density.
For power, we use up to 8 22.2 volts, 5.2 amps depot batteries connected in parallel with custom-made PCBs to a DALI BMS, which balances and protects the system. Later, a custom distribution PCB regulates to the necessary voltages.
Communications are managed with 2 Rocket Prism 2AC at 2.4 GHz, with a 90-degree sector antenna at the base and an omnidirectional one on the rover, achieving seamless operation at more than 700 meters.
We're currently working on a new design of the rockers that features a better positioned shock absorber and a new rocker frame to better withstand the loads of omnidirectional movement.
For control, a Jet Sonori Nano running ROS2 Humble manages main sensors and connects via WART to 2 custom PCBs nesting 1 TNC 4.1 each, which control the others via CAN and other sensors and motors with low latency and precision. In the arm, the shoulder and elbow are powered by 2 variations of our motor designs, with a higher stator and stacked gearboxes for greater torque output.
The structure of the arm consists of carbon fiber tubes to balance strength and weight, as well as regular and carbon-filled PETG 3D prints. The base of the arm is a custom worn gear driven by a stepper motor, which holds the base where both the shoulder and elbow motor rest. The elbow motor uses a belt to drive movement while minimizing the load on the shoulder motor. Belt systems are also utilized in both the forearm and differential grip mechanism, which gets to a total of 6 degrees of freedom. The basic gripper has one servo-driven finger with soft tips. It is easily interchangeable for the Science Mission Auger. Currently, we are implementing a gazebo simulation with movement for inverse kinematic to improve further the maneuverability of the arm, as well as detecting collisions with itself and the chassis. Control for the whole rover will be facilitated with an on-development user interface to see the state of all motors and general information. For manipulating objects, the rover also assists with alignment and height adjustments. This is possible due to 3 single-point LiDAR sensors at the front.
For autonomous mission, the rover employs GNSS data from a differential set F9P, with up to 10mm coordinate precision to determine its position and create a grid of potential roads. It uses Dijkstra algorithm to assign cost metrics and select the optimal path, carefully avoiding major obstacles while charting a precise course to its designated coordinate.
The rover's sensor suite continuously monitors its surroundings. The RP LiDAR S3 scans for distant obstacles, and the RealSense D455 detects finer terrain irregularities. High-resolution cameras are used to detect Arucotex. In addition, we use YOLO V4 to identify the bottle, and TensorFlow to recognize the hammer. When an object of interest is confirmed, the rover navigates towards it, halts, turns on a work-in-progress LED screen, and then calculates its next route segment.
Venture features a sample extractor auger with a 10 cm digging depth, powered by a 35 kg capacity server within a gearbox. It has a storage unit for up to 20 grams of soil and rotates clockwise to collect and counterclockwise to discard.
Following the placement of the sample, the analysis begins. The soil is held in a Petri dish mounted on a 2-axis arm. The arm moves the dish to the spectrometer stage, where light data is collected. It then rotates the disposal stage. This modular setup allows for future UV light analysis.
Our onboard lab uses UV light to detect life. Organic molecules like FAD, NADH, and chlorophyll react to UV light, helping us to identify biological material in the sample. Additionally, we use a spectrophotometer to analyze the spectra of samples. This helps us identify key elements and minerals associated with life. We're doing a database in Python to identify them in a solid sample. Finally, we conducted a preliminary remote sensing study to characterize the MDRS conditions, and this data is essential for assessing habitability before the mission.